I think we have a mutual time on like Tuesday morning or something for everybody. But if I can do it with Jeff, I'll schedule it probably, and then if it works out with Jeff, and then for people who can't make it, you can watch it on TV. So that's how we'll do it. Thanks for reminding me. Okay, so back to rheology. We're talking about advanced constitutive equations. And so this is what we've been leading up to. And I think there's a lot of really good stuff here. The way I have it laid out is I'm going to show you how the various pieces fall together and how we get to nonlinear constitutive equations. So there's going to be a fair amount of me doing some calculations over there. So I just want to maybe warn you of that, but I'm going to also point out along the way what is the point of each calculation we're making. So what we did last time was we saw, based on the generalized linear viscoelastic model, where the problem was. And this was the problem that gave us dependence on frame of reference for that model. So this is the generalized linear viscoelastic model. And what we did was we looked at it and did a little bit of a manipulation on it to show what strain variable, what strain tensor was being used in this expression. Now actually, in, let's say, a mechanical engineering approach to this same subject, they would have started right in on strain tensors. Because when you deal with solids, strain is sort of the natural variable. Because let's say you have a solid block of rubber. When you strain it, when you put it under strain, meaning deform it, it requires a certain stress, a certain effort on your part. And so there, let's say the simplest constitutive equation in solids is stress is proportional to strain, the Hooke's law. Now we started from liquids, which is a rate dependent. And so for the Newtonian fluid, the stress that it takes to move this top plate when I have a fluid between them is proportional to the rate of deformation. And so we started out with strain rate, and we ended up with a constitutive equation with strain rate in it. They would have started out with strain. And we're going to get to new strain measures, in fact, today. So we did an integration by parts on this constitutive equation. And we got a different version of it that now has this strain tensor in it. So we integrated gamma dot and got this strain tensor. We differentiated G and got this new function, which is called the memory function. That's just vocabulary. And we got a new equation that's not on the surface any better for us. Because as far as we've been concerned, what we want these equations for is to be able to calculate stress. And in our, let's say, our material functions, we mostly know the velocity field, let's say shear or elongation, and we preferred the old way, which was a constitutive equation that had strain rate in it. So it doesn't, maybe on the surface, look like a useful thing to have done, but what it has done for us, it has shown us what the strain measure is. And that's our taking off point for today, which is how to develop a new, well, first of all, to talk about what's wrong with this strain measure, and second, how to develop a new strain measure that will not have the same problems as the generalized linear viscoelastic model. Okay, so again, last time I stated what this strain tensor was. This is the infinitesimal strain tensor, and it's defined by this combination of variables. And this u vector, this displacement vector, is just taking into account the change of position of particles in a material that's deforming. So for instance, if I consider a very simple motion, it's not really a deformation, but a very simple motion of taking a cube of fluid, or a solid if you like, and rotating it through an angle phi, then I can identify any point in that fluid, point P, and its location will be a function of time. So it's here at this time, and it's up here at that time, and those are at two different times. And mathematically, I can identify that location by this vector r, which is a function of time t, and then at a later time r prime, which is the location vector at time t prime. Okay, so back over here, r, which is, I could also write this as r prime, which is r at t prime, minus r is the displacement vector. So if I draw a straight line between these, I get my displacement vector, and it's taking into account the change in motion. If I sneak ahead at one slide and I do a deformation that includes a change of shape, here's the case where I've just rotated, let's say an ellipse, and here's the case where here's the old state, and in the new state I've rotated but also deformed and changed the shape. And so again, this point P at time t is given by that vector r, and at time t prime, a later time, it's given by this new vector. The difference between them is the u. And here's r prime at a later time. The difference is u. And you can see that there's some information about the change in shape and the change in the orientation of our particle. Now, this particular choice, though, of how to take into account change of shape says that it takes into account both rotation and deformation. So for instance, in this case, where there is no deformation, there's still clearly a change in u. There's still a grad u. So I want to do a little bit of exercise with this math so that you can see what it is and so that you can see why this is a bad idea for how to take into account our deformation. Okay, so let's consider this case of just a simple rotation, and let's calculate gamma. Okay, so let me title this, let's say, to see what's wrong with gamma, we'll calculate it for a simple motion. Okay, so this is going to be a little bit unfamiliar, so that's why I want to go through an example. So gamma is equal to del u plus del u transpose. So if I have u, I'm good, right? If I have u, I can take these derivatives and I'm good. So u is equal to r prime minus r. And so if I have r and r prime, I'm good because I can subtract them. And here they are. Okay, so here is r, and I've written, actually this is the rotation within a plane. And so I'm not going to be worried about any changes in the z direction. There aren't any. So I've been very formal both in the book and in this example. R bar is actually not, our r is from the origin out to a point. And this r bar is from the z-axis out to a point. And so we can actually use the r bar as a simpler calculation than having to do this angular r, because we're just doing a rotation in a plane. So if I would write r prime, the vector I'm looking for, is really equal to this r in the plane plus whatever the coefficient is in the z direction times ez. And r is equal to this r in a plane plus whatever the z coefficient is ez. And if I subtract them, I get the same thing. I get r prime minus r is equal to r bar prime minus r bar, because these two are equal. So all I'm saying is I'm doing a slightly simpler calculation. Instead of doing from my origin out to my point, I'm doing from the z-axis out to my point, so I can just stay in 2 dimensions. so now I've really simplified my case. I just need these vectors, and they're right here. So for instance, R, looking just at the left side, R bar is a vector that has an x component and a y component. And the x component is R cos beta. And the y component is R sine beta. Okay, so very simple. There's the y, there's the x, no z component. And likewise over here, we can do the same thing. R bar prime, meaning at t prime, is equal to R bar, this is the vector R bar prime, is equal to the magnitude R bar prime actually it's the same magnitude, so I can just use R bar. And then the x component is going to be cosine of the combined angle. Okay, so if I drop this down here, this part here is cosine of the combined angle, this part is sine. So what do I have here? X is cosine psi plus beta EX plus R bar sine of psi plus beta EY. Now we've got these R and R prime, so we can get U. And I'm going to let me first expand this, this product here. So R bar prime is equal to cosine, R bar cosine psi plus beta, R bar sine psi plus beta 0. And I can expand these using the sine and cosine of the sum of angles. And so I get R bar. The cosine one is cos minus sine sine. So it's cos psi cos beta minus sine psi sine beta. And the sine one is sine cos plus cosine. Sine psi cos beta plus cos psi sine beta. Okay, so I want to actually write, all right, now I'm going to calculate U, but I'm looking at my notes and seeing that what I'd like to do is relate this back to the initial x and y coefficients of this point P here. Okay, so I haven't set myself up very well here, unfortunately. Okay, I want to write this, and I've also got the R, of course. I've got R bar is equal to cos beta R bar sine beta 0. And I'm going to subtract them But I want to write this a little bit differently because I want to go back to using the notation where, again, looking back onto this plot, x is equal to r cos beta. And y is equal to r bar sine beta. I want these in there because I'm eventually going to be taking derivatives with respect to x and y, and I want to show those up. So the beta part is the angle that's related to the motion at time t. And we can relate that to the locations of the particle at that time. And I'm going to substitute these in here. This cos beta, I'm going to write x. And this sine beta with the r in front, I'm going to write y. And like here, x, and here, y. So notice that the beta refers to the initial state. The psi is the angle of the motion that we're trying to describe. So the psi is going to be left over when we're done, but the beta is just an arbitrary angle that defines my initial point, and instead I want to define that by the x and y. All right, so I hope I haven't made that too confusing. All right, so now I want to do u. Okay, remember where we're going. Gamma is del u plus del u transpose, and u is r prime minus r. So we've got r prime and r here. We just need to subtract them now. And so we've got u equals r prime. Okay, so I'm copying from the out of your sight. R cos psi times x. No, excuse me, no r anymore because the r goes with the r cos beta is x, so I end up with x cos psi. And r sine beta is y, so I get minus sine psi. And then when I subtract r, I subtract an x. Times y. Here, right? Thank you. And then r cos beta is x, and that leaves me with a sine psi plus y cos psi. And when I subtract the r, I get a minus y. Wish I could show both of these at the same time here. Okay, so r cos beta is that x, cos psi. R sine beta is the y, sine y. And then the minus x is this. R bar sine cos beta is the x, sine psi. R bar sine beta is the y, cos y minus y. All right, so now we're in the good shape. We now need to do grad u. Grad u is, of course, d by dx, d by dy, d by dz. So the derivatives go across the rows, and the thing we're taking the derivative of goes down the columns. So this is ux, this is uy, and this is uz. So when we take this is ux right here. When we take the derivative with respect to x, we get cos psi minus 1. When we take the derivative with respect to y, we get minus sine psi. When we take the derivative with respect to z, we get 0. Okay? So the derivative with respect to x is cos psi minus 1. The derivative with respect to y is minus sine psi. And the derivative with respect to z is 0. The derivative, this is uy. The derivative with respect to x is sine psi. The derivative with respect to y is cosine psi minus 1. And the derivative with respect to z is 0. And uz is 0. Okay, so this is just carrying out the usual operations for grad u. And now we would take grad u plus grad u transpose. So that means that gamma grad u plus grad u transpose. This plus its transpose doubles it. This plus its transpose becomes 0, 0, 0. This becomes double, 0, 0, 0, 0. Now this is our final answer for the strain tensor. And what this says is that for the strain between time t and t prime, there is a strain that in fact is a finite strain. Okay? So for instance, if we took this strain measure and put it into a simple Hooke's law model, Hooke's law says the stress is proportional to the strain through the modulus. And if we use this strain measure, then this tells us that the stress is equal to the modulus times this tensor when we have this simple rotation. And that's a problem, because all we're doing is rotating a block in space. Okay, all we're doing is rotating a block in space around the z-axis, and this says that there's some sort of a stress that's been generated. Okay, this is the problem. This is what's wrong with this model. So this predicts that simple rotation without deformation, without change of shape, generates stress. This is wrong. So that same tensor is written here. Okay? If we put it into the generalized linear viscoelastic model, it also predicts that the stress is a function of the angular position of the block of fluid, and that's garbage. Okay? And this garbage is what we need to fix. And as I've been pointing out, this makes this erroneous prediction because this definition of the strain tensor takes into account the position of every particle at every time. And there are two things that happen when the position changes. Sometimes following two particles from one place to another is a good thing because there's a deformation that takes place. And let's say if I had a sample and I'm just stretching it, if I just looked at these two particles and said, okay, at time t they're here and at time t prime they're here, then the ratio of those two lengths, or the difference of those two lengths, would be a measure of the deformation of the sample. But the problem is that when all I do is rotate, the change in the position, the vector position, the orientation of that vector is not telling me anything about deformation. So it's a mistake to use a strain measure that takes into account rotation like this. We want one that only takes into account stretch. And that's what we have to work on now. And it's going to take a little bit of effort because anything we can think of, you know, like in a complex deformation, there's going to be rotation and deformation. Okay, so we need to figure out a way to mark the change that happens in a blob of fluid under any circumstance, whether it's a rotation or a change or a contraction or a stretch. Okay, so let's see how that works. So this is how we're going to do it. We're going to define some deformation tensors, and then we're going to apply a principle from tensor calculus called polar decomposition, which will allow us to take the rotation out. Okay. So first we're going to develop a complete tensor, strain tensor that will take into account, just like gamma, both stretch and rotation, and then we're going to take out the rotation. Okay, so that's the beginning on this slide here. All right, so now we're going to consider a general deformation, something like, we're going to consider it the same way that we considered the simple rotation we just did. We're going to take a blob of fluid at time t prime, and now a blob of fluid at time t. And we're going to follow two particles, P and Q, and at time t prime, they are separated by a little, they're very close to each other. They're separated by a little vector dr prime. At time t, they're separated by a little vector dr. You know, P maps to P and Q maps to Q. And here are the vectors that we would use for the infinitesimal strain tensor, but we're not going to use them this time. This time we're going to concentrate on the little vectors dr and dr prime that map the material just within the body, map the change of shape that's happening in that body. Okay. So I'm going to begin this derivation by saying we seek strain measures that can be made independent of rotation. Okay, now this is following the usual nomenclature in rheology. R prime is the position of our particle at time t prime. Now, we have a lot of particles. It's a fluid. It's many, many particles. So we need to know position of what particle. And the way we do that is we say that R prime is the position at time t prime of the particle that's in the location R at time t. It's the position at t prime of the particle that at time t is at location R. So this R is the particle identifier. So we can think of this time t as sort of a reference configuration, a reference shape. And we always need that for strain. You always have to say, what's your starting shape? What's your stopping shape? So this is going to be our reference shape is at time t. All right. So here we go. Let's write these out. All right. We have two locations. We have location R, which is just a position vector at time t. And we have a position vector at time t prime that has coefficients as well. So I'm just saying these are their names in the xyz coordinate system. Likewise, we have these little differential vectors, dr prime, this little vector that notes the relative location of two particles. And this will also have coefficients in this coordinate system. Now, to relate these two states, I'm going from the reference state to the current state. I need to put together a transformation. And to do that, I'm going to use the chain rule. Okay? The vector r prime is a function of t prime and r. So using the chain rule, I can write these little changes in location in terms of the initial location. So for instance, I can write dx prime as a function of x dx, dy, dz, okay? Because x prime is a function of r. And so this is dx prime dx, dx prime dy, dx prime dz. Because the position at time t prime is a function only of what particle you're talking about and time, okay? We can write it using the chain rule of multivariable calculus as the partial derivative of the function with respect to all the variables, each of the three spatial variables, times the differential in that direction. We can do the same for y prime and z prime. Partial y prime dx dx plus partial y prime dy dy plus partial y prime dz dz. Same idea. Now we can be a little tricky with our Einstein notation here and write this a little bit more compactly. For instance, we can write dx prime equals partial x prime with respect to the vector r dotted with dr. Let's see if that's right. Partial x prime with respect to r, well, the coefficients of r are x, y, and z, okay? So I could say with respect to x, I, e, I, dot d, the coefficient of r is x, xj, ej, like that. So when I dot these together, I get delta ij. I get dx prime dxi dxi. So these two match, and that's what we have here, right? These two match, these two match, these two match. These two match, these two match, these two match. This is 1, 2, 3, which I could write as dx prime dx1, which is x, plus dx prime dx2, which is y, plus dx prime x3, which is z. So that is, in fact, the same thing. So the chain rule written in Gibbs notation is just dx prime equals partial x prime dr dot dr, and I can do the same for y. dy prime dr, the vector dotted with dr. And I could do the same with z. dz prime equals partial z prime dr dot dr. Or I can combine these three together and say dx prime, the vector, is equal to partial x prime, the vector, with respect to r dot dr. This x prime is really, I should write this as r prime, because the coefficients of r prime are x prime, y prime, z prime. I'll rewrite that. dr prime dr dot dr. So in some ways, I know that looking at that little development there, all I did was use the chain rule. But what I did was I related at the end of the day, excuse me, this is r prime here as well. It would help if I weren't making mistakes today. These are the same thing, so I'll just cancel that one out. dr prime here. Okay. What I've done is I've related this vector to this one. Now it kind of looks like, well, this just cancels with that and I've done nothing. But actually, it's very formal. There's a dot product here. And this ratio, this is a tensor. Okay? This is a tensor that tells us how to relate the initial location of this vector that separated these two particles from the final location. And that's what we were looking for. We were looking for a tensor transformation that would take this to that. And if I picked any two other points, it would tell me how to transform this body, any 2 points in the initial body, to this final body. This is called the deformation gradient tensor. Okay? So dr prime equals partial r prime with respect to r dot dr. If this is called f, then we have dr prime equals f dot dr. We can also go backwards from, instead of going from, if I know dr and I know f, I can get dr prime. I can also go from r prime to r by doing a little linear algebra here. If I define f inverse as the inverse of f, so that means that f dot f inverse equals f inverse dot f equals the identity tensor. Okay? We can use that to calculate the inverse here. Let's say I left multiply everything by f inverse. Then I get f inverse dot dr prime equals f inverse dot f dot dr, but this is just the identity tensor, and so I get dr. So f inverse dot dr prime is equal to dr. So this is what these tensors look like. The deformation gradient tensor f is dr prime dr. The nomenclature, I admit, is a little bit awkward because I switched from r's to x, y's, and z's, but I want to match the rest of the world. These are position vectors, and so that's why we're used to thinking positions in terms of x, y, and z. If you write it in Einstein notation, you might write it like this as r. That would be fine. Fundamentally, it's a gradient just like the velocity gradient. The thing on the bottom goes across the rows, so these have no primes on them. The thing on the top goes down the columns, so this is x prime coming down the column, y prime coming down the column, z prime coming down the column. F inverse, which we can go back and do the chain rule and figure out that F inverse is equal to dr prime is equal to this tensor. These are changes that we can calculate for given flows. So for instance, we could calculate the inverse deformation gradient tensor or the deformation gradient tensor for shear flow. And all we need, see what we're doing here, is we need an expression for the position of the particle at time t prime in terms of where it was at t. That would be something like this, okay? Where is the particle? This is the position of the particle in shear flow as a function of time. If its initial place, if it started out at a position x, y, z prime, where is it after some time t? And so this, all we need is this expression, and we can take the derivatives that we need to get f or f inverse. So this is just shear flow occurring. So in shear flow, the y and z positions never change. The x position is the initial position plus the velocity times time interval. And that's what this is. The velocity is gamma dot times y. And the time interval is t minus t prime. So we could very quickly do that example. In shear flow, if we want to calculate f, f is dr prime dr. And we have it here. We have x prime plus t minus t prime gamma dot naught y prime is equal to x. We have y prime equals y. We have z prime equals z. So now we need, for instance, we know we're going to need f is equal to dx prime with respect to x, dy prime with respect to x, dz prime with respect to x, dx prime with respect to y, dy prime with respect to y, dz prime with respect to y, dx prime with respect to z, dy prime with respect to z, dz prime with respect to z. So can you help me out? What is dy prime with respect to y? 1. There's the equation right there. Take the derivative with respect to y, you get 1. How about dy prime with respect to z? 0. How about dz prime with respect to y? Z prime with respect to z? X prime with respect to z? 0. X prime with respect to y. Okay, so here, when we start taking, let's leave that off for a second. Z prime with respect to x, 0. Okay, so we have maybe some interesting ones here. We need x prime with respect to x. If I move this over to the right, but there's no x in it, 1. And now these are the tricky ones here. X prime with respect to y. Yeah, let's be formal about it. You are correct. Okay. What we actually have here is x prime as a function of x, but when we're taking let's see. Is that what I want to do? I want to write this entirely in terms of x prime as a function of things in the past. So if I solve it for x prime, y prime, but y prime is equal to y. So this is now a form where it's the time x position at the prime. Everything on the left is at t prime. Everything on the right is at t. And now that makes it more clear how to make the derivative. dx prime with respect to y is minus t prime gamma dot naught times 1. And likewise, y prime as a function of x. If I solve for y prime, again, only in terms of things in time t, I get x prime minus x wait, let's see, what do I want to do here? Equals t prime minus y prime equals x minus x prime Well, I'm painting myself into a corner for some reason. Oh, I see. I'm painting myself into a corner. Excuse me. I want to take dy prime with the function x, which is right here. The partial derivative of y prime with respect is 0. Okay, so going back in order and hopefully less confusingly, the x prime we calculated here. So we get the whole first column from this expression. With respect to x, we get 1. With respect to y, we get this coefficient. With respect to z, we get 0. The other two are easy. Here's the expression for y prime, so we get 0, 1, 0. Here's the expression for z prime, so we get 0, 0, 1. Sorry for that confusion. So this is the final expression for F in shear flow. This is sometimes written a little bit differently because we can relate this quantity to the strain. If we define gamma as the integral from t prime to t of gamma dot naught dt double prime, we get gamma dot naught t double prime evaluated from t prime to t, and we get gamma dot naught t minus t prime. And so we can write F as 1, 0, 0, minus gamma 1, 0, 0, 0, 1. There's a table in the book of inverse deformation gradient tensor for a variety of standard flows. So the one we just derived here, F, there it is, 1, 0, 0 minus gamma 1, 0, 0, 0, 1. The inverse tensor, which you can get by from the definition and taking the derivatives, is very similar but with a positive sign. And if we did the same for uniaxial elongational flow, we would get these two tensors. And the one that we did for counterclockwise rotation around the z-axis is equal to this one with these sines and cosines. Now, these two tensors have both rotation and stretch in them. So our next task will be to create deformation tensors that don't have rotation and stretch. And that's what some of these other entries in the table are. So we'll get to these next time. Okay? So that's it for today.